Now I'm on. Here we go. Good afternoon, everybody, and welcome to the Climate College. Great to see so many Earth scientists here this time. Firstly, I'd like to acknowledge the traditional owners of the land on which we meet, the Wurundjeri people, and pay my respects to the elders past, present, and emerging. Today, it's my pleasure to introduce Craig Bishop. Craig is a professor of meteorology at the School of Earth Sciences. He joined the school last year, having spent most of his career in the United States, and most recently at the Naval Research Laboratory in California. Among other achievements, Craig is a founding co-chair of the World Meteorological Organization's working group on predictability, dynamics, and ensemble forecasting, and is also a fellow of the American Meteorological Society. Having completed his PhD at Monash University, Craig returns to Melbourne to continue his work on ensemble prediction, of which his techniques are used by forecasting agencies around the world. Today, we'll hear from Craig on using observations to improve ensemble-based climate projections and the ensemble dependence transformation. Great. Thanks, Craig.
Thank you, Sonia. It's a pleasure to be here. It's just great to be back in Melbourne, and the idea of this college is just great. I love the way it's like pulling together meteorology and economics and everything like that. So just great to see. Before you're probably all used to like forecasting models. There's computer models that make weather forecasts, and you probably know that there's computer models that also make climate forecasts. And I just wanted to throw a question out there just to see what responses I got. Like, suppose you had one kind of perfect model. Yeah, it could be like a replicate Earth. Yeah, so it just exactly represents the physics that governs the ocean and the atmosphere on our planet, and that you could also feed it representative concentration pathways, so trajectories of greenhouse gas concentrations. But you only had one of them. Would that be enough to tell us everything we need to know, like how strong we need to make our dams, how big our dams need to be to plan ahead if we just had one model? What do people think about that? Would that be enough? Could we figure it all out with just one simulation? Yeah, okay, lots of people shaking their heads because that's one of the points I want to come to. Okay, so this is, as you probably know, the leading research centers all over the world are producing numerical models, computer models of the atmosphere to make climate projections. They're not that dissimilar to the models that are used to do weather forecasts. They have sort of more sophisticated representations of the land surface and the biosphere and a few other things, but in many respects, they're like weather forecasting models. And people have agreed on representative concentration pathways. So that's of greenhouse gases, like likely scenarios of increases in greenhouse gases. And different groups have contributed in forecasts, assuming those greenhouse gas concentration pathways. And you end up with not just one projection of climate, but many. And they come from different models, from different centers, and they do not agree with each other. For example, a little story. So low clouds, like stratus, they're exceedingly effective at reflecting shortwave radiation. Yeah, and it turns out there are huge banks. I don't know if any of you have been to San Francisco, there's a good chance that you went there and it was cloudy. There was all this stratus and it was cold. That bank of stratus is not just in San Francisco. It stretches all the way down the West Coast, well, not to LA, but sort of that northwest part and way out to sea. And it's reflecting an enormous amount of light. There's another big bank like that off South America as well that's reflecting, very effective at reflecting shortwave radiation. And you can show that if those low-level clouds, if they increased their area by 4%, that would offset the warming due to greenhouse gases. But if it went the other way, if, say, 50 years from now, there's 4% less of those low clouds, and that was the only thing that changed, then, you know, climate warming would be much, much worse. It turns out that all the models actually disagree about what's going to happen to the low-level clouds to some extent. There's a lot of disagreement about that. So there's this big uncertainty in these climate projections. We know there's a lot of sensitivity, and this is just a small piece of work that I did with Gab Abramovitz and Ned Horton to try and think about how we can use the historical record of observations to get a better idea of what's going to happen in the future. So one of the key things we wanted to get for this was a climate probability distribution. And I'll describe what that is and talk about why it matters and why it, in some sense, hides. There's a question of observability of a climate probability distribution. And it's somewhat hidden. And I'll talk about that a bit as well. So I'll talk about the relationship between observations and the mean and variance of this. It's kind of a theoretical concept, this climate probability distribution, because on our planet, I don't think we can directly observe it, or at least all characteristics of it. And then there's these ensembles from CMIP 3 and CMIP 5, and that they do not satisfy, they do not really look much like a climate probability distribution when you compare them with observations. Then I'm going to show you, and I won't go into the details of this, it's a bit mathematical, but you can come up with this transformation of the ensemble that makes the projections much more like a CPD, a climate probability distribution ensemble projection. So, and then I'll show you some tests. They're actually, even though we're talking about things in the future, there are some fairly convincing tests you can do of whether the method's working or not, and then I'll conclude. So, the climate probability distribution gives the probability of observing things like values of temperature, wind, rain, or other environmental phenomenon, sort of like, say, next year. Yeah, so I'm not talking about there being any initial condition constraints here. It's just given this climate, the current trajectory of greenhouse gas forcing that we've had, if that's the only thing you knew, what would be the probability of having droughts, of having extreme rainfalls and stuff like that. So it just gives you the climatological probability of everything you can think of, including low time period things like an interdecadal oscillation. So climate change detection, attribution, and impact assessment requires this climate probability distribution, not just the mean. You're probably familiar with the idea that when you have a distribution, you need, the mean is kind of a measure of the center of the distribution, but there are all these measures of the spread. You could have the variance, there's a kurtosis, there's a skewness, just lots of different ways you can measure the spread. Now, if we had reason to believe that the climate system was static, you could actually get this climate probability distribution from historical data. You know, you could just go back in time and count the frequency with which things were observed, and that would be the frequency that happened. But we're in a situation where we have very little reason to believe that the climate is static. We know we're pumping these gases into it that have a very different radiative properties than the gas concentrations we had, say, 50 years ago. So, you know, we've got this CPD thing must be changing, yeah? But we've just got one realization of what all the possible weather you could get for the greenhouse gases that we have in the atmosphere at the moment. Yeah, so greenhouse gas concentrations are rapidly increasing, and current atmospheric concentrations of carbon dioxide, methane, and nitrous oxide have increased to levels unprecedented in at least the last 800,000 years. And I'm not sure if this is quite clear yet, but you can show it is impossible to determine all the aspects of the CPD, like right now, from observations alone during this type of climate change. And so here I want to I think you can show you can get closer to it by using ensembles and observations, and that's kind of what I'm going to try and go for here. So what is this climate probability distribution? I was just telling you, you can't define it with observations, yeah? But we have lots of things like that, where we only can know it conceptually, yeah? An equilateral triangle is like this, yeah? We can never draw a perfect equilateral triangle, but we can describe what it is. So, so let's do that. Let's think of the thought experiment that defines the climate probability distribution. So for this, imagine a very large number of Earth replicates that experience the same orbital solar greenhouse gas forcing as our Earth. Yeah, so pretend you're God, you have 1 million universes, and all of them have an Earth. But on these Earths, say the butterflies are flying in different directions, which, as you might have heard in chaos theory, will ultimately lead to different realizations of weather, different realizations of MJO, of the Madden-Julian oscillation, different realizations of interdecadal oscillations. All that stuff will be different. Yeah? So this is a property of a chaotic system. But what's common to all these imaginary Earths are that they have the same trajectory of greenhouse gases. So if you had this huge ensemble of replicate Earths, they're perfect models, if you like, then at any time along this trajectory of increasing greenhouse gases, you can know the frequency of anything. Yeah, you just have to find, you know, suppose I've got 100 million realizations of this, yeah, of these replicate Earths, then, you know, I could find a 1 in 100 event by finding the million members that have that thing happen. Yeah, that would be a 1 in 100. But, you know, just all these frequencies you can compute from that ensemble. And I guess part of what I want to get at, so you can think of this ensemble of really good models going forward in time. And as the greenhouse gases change, you might get things like the actual climatological variance might decrease or it might increase. So it's not just the mean, yeah? You can have these different distributions. If you're talking about rainfall, we might start seeing more extreme events. So the tails on the rainfall might get bigger. But we are only on one Earth, yeah? So we only ever get to see one realization of this climate probability distribution. And the greenhouse gases, they're changing the climate probability distribution. It's not really, you know, they're not really affecting the specific weather on any particular day, but it's this climate PDF. So just as a simple visualization of this, let's suppose this is some sort of weather anomaly. This is just made up numbers here, just to get across the concept. We're going from 1900 to 2000 here. I could have taken it further. But yeah, let's suppose we had all these replicate Earths and this weather anomaly was in some sense increasing. So we'd have this increasing mean and all these different replicate Earths. And one of those Earths would be our Earth. And let's pretend that's the black line there, yeah? So in this particular example, the only thing that's changing is the mean. I didn't let the standard deviation change. But in principle, this standard deviation might change as, say, the greenhouse gases change. Yeah, and I guess, you know, at any instant in time, you know, this variance could get big, but actually you wouldn't be able to tell how big the variance was from just one Earth, yeah, at that particular instance, because, you know, you've just got this one realization, and it's hard to compute a measure of variance if you've just got one realization. You need many realizations. So that's part of what I mean by it being hidden. But in this particular example, that variance is changing slowly. So you could get some information from one Earth. So, all right. Just using this little example, what I'm going to do is I'm just going to state two very simple properties of the relationship between this climate probability distribution and our Earth. Okay, so one is that you can show that the mean of the distribution of replicate Earths, in this case it's the blue line, that is the linear combination of Earths that minimizes the mean square distance from our Earth's observations. So if you had this replicate Earth ensemble, which is the results from each ensemble member is like one of the colored lines on this diagram, and you wanted to predict, you know, going out, that something that would kind of be close to the this black line, the best way of linearly, when I say linearly combining, I just mean you do something like 0.1 times line number 1 plus 0.05 times line number 2, etc. Like that. If you're trying to find out what's the way to weight these different ensemble members to minimize the distance from our Earth, it's just the sample mean. You give them all exactly the same weight. Very, very simple. Yeah. And the error variance of that forecast is actually just the climate variance. So the mean square distance, so for each, so there the black line, you can see it's that far away from the blue line. I can square that value, and I can do that all the way along the line. And then if I average that, that's the mean square distance. Yeah, so one of the things you can actually show, so that's one thing. So to minimize that distance, that's the sample mean. And then the other thing, provided this variance of the climate probability distribution, so I'm trying to indicate the width of the distribution there, provided that width isn't changing very rapidly through time, then another property you'll get is that the time average of the variance of the replicate Earths will equal the mean square distance of the climate forecast based on the mean of the replicate Earth. So basically, if I look at this mean square distance of our Earth from this blue line, that will be equal to sort of a time average of the variance of this ensemble. That's all. So the variance of the ensemble should be equal to the mean square distance of our Earth from the blue line. So you've got those two things. So this would be the idea, you know, if we had these perfect models, we could pretty much say everything we needed to know about future climate. And you can also ask, well, if we had this perfect set of models, how would they covary with each other? So what I'm trying to indicate here is this might be some variable. This could be temperature in Melbourne from one of these replicate Earths. And then this could be, I can subtract from that the temperature that we actually observe on our Earth in Melbourne at a particular time when they're both taken at the same time. And this would be from the second model. So that's, if you like, a prediction of the temperature in Melbourne, and that would be the observation of the temperature in Melbourne, and so on. So I could do that for all my replicate Earths. And you can show that another property of if you had this ensemble of perfect models, or perfect Earths, then what you'd find is that the average square distance between our Earth and one of these other models is actually twice the climatological variance, and the covariance between this sort of error of the second model and say the difference of the second model from our Earth and the difference of the first model from our Earth, that would actually be equal to the climatological variance. So the models, they actually are correlated with each other, and they have a covariance. The reason, yeah, I don't know, maybe that's getting a bit technical, but it's fairly easy to understand. The reason, even though all the models are independent, the reasons you get this covariance of the errors from different models, it's because, like, you know, if you take a particular time when our Earth is extreme, then basically on those occasions our Earth is extreme, then all the other models have the same signed error. And that's why these off-diagonal terms, you know, are positive, because the errors of other models tend to go together. Okay, so this is this ideal forecasting system. When we look at the CMIP ensembles, I think this is CMIP 5. Yeah, CMIP 5. And we draw that covariance matrix. So we're basically computing this thing here. So what we should see is all the numbers down the diagonal should be the same, and all the off-diagonal elements should be equal to 0.5. We don't see that at all. We see these sort of boxes at the center. And what's going on here is like, these are a whole bunch of models contributed by CSIRO. And you can see that the errors, so the difference of those trajectories compared, so these climate forecasts are started back in about 1890, and then they march them through to sometime after 2100. And so we can get to compare those model forecasts with our actual observations for the last 30 years. And so you can see how those differences between the models co-vary with each other. And what you see is that the errors from, say, one group, CSIRO here, are all highly correlated with each other. They have correlations much higher than 0.5. You can see the color scheme here. So those correlations are up around 0.8 or something. This is just the correlation part, not the covariance part. And you can see, it's not just CSIRO that happens to. Here's HagJam. These are all models from the British Met Office. So they all have those characteristics. And the off-diagonal elements, actually, instead of saying you should see correlations of 0.5, you actually see correlations much less than 0.5. So it just doesn't, this is nothing like an ensemble of perfect models. You can also say that the mean of that CMIP ensemble is not the linear combination that minimizes the error variance. And you can also show that the time average of the CMIP ensemble variance is not equal to the mean square error of its mean. If we look over the last 30 years, neither of those properties are satisfied. So what Gab and I did was we said, okay, well, we've got this historical record. Maybe there's some way we can transform these ensemble members so that they would have those two properties. So this is the form of the transformation we're going to take. So xi is, let's suppose we're doing this for Melbourne. Yeah, so let's let xi be the temperature from the ith model from the CMIP ensembles. Let me see, did I list the models? I didn't have that, did I? I've got a list of the models somewhere. Where's that? No. Sorry, I'm just going to load this. Yeah, so for example, that's a list of models we had. So each of these centers is contributing a certain number of models. And so for each of those, we're going to take that a forecast of an observation, and what the observation's of is, you can take that to be whatever you like, but let's say it's temperature over Melbourne. So that's from the ith model. We might have an ensemble of 100 models. This X bar there, that's the sample mean of the predictions from each of the models. Alpha is a constant, beta is a constant. This mu e is a mathematically determined minimum error variance estimate. So it's the set of weightings that would minimize the distance of the verifying observations from sort of a forecast made basically back in, initialized in 1880. But the main thing I want you to get from this is that what we end up with is this transformed ensemble member, this xi. I should use this, shouldn't I? Where is it? This guy. Nope. I can't. Move to the left. All right. Yeah. Okay. So that I can't really point at it so well. That xi thing, that tilde thing is that will go up and down as that xi will go up and down as this xi goes up and down. So there's a really direct connection between this transformed ith member and this ith member there. And we do it in a way so that the weights sum to 1, and also that this mu e is, you get it from that, and this mu e, that's the minimum error variance estimate. So when I say minimum error variance estimate, I mean what linear combination. So if I'm just going to take each of these ensemble members and multiply them by a number, how can I do that in a way so I get a trajectory that minimizes the distance from the observations that were actually observed on our Earth. And then the other characteristic we want is that this same these weights just add to 1. The other characteristic I want is that these weighted square differences between each ensemble member and this minimum error variance, that actually equals the mean square distance of this minimum error variance estimate from the OBS. So this is basically ensuring that the spread of this transformed ensemble is equal to the mean square error of its mean, which was one of the other property we wanted for this replicator, this climate probability distribution type ensemble. And all these parameters, actually, I showed you that A matrix, which was kind of the error covariance. So it's all closely related to that. So where was the A matrix? That was the A matrix. Well, that's the correlation form of the A matrix. And then once so because these weights are all positive and they add to 1, you can actually treat these weights as being like the probability that that member is actually a true replicate Earth. And you can, so the ensemble is created by sampling x tilde I with frequency wi. So this is, you know, it might be say 0.1 or something. Then you sample that member 1 out of 10 trials. And that's going to be like a replicate Earth in that the ensemble I create by doing that will have a sample mean whose minimum error variance estimate, whose sample mean is the minimum error variance estimate, and its variance will equal the error variance of the sample mean. So you'll have those two properties. So I'm going to show you 2 tests. One's with historical observations, and the other's with, well, I'll describe it when I get to it. But this first test is, what we're going to do is take 24 CMIP3 models. We're going to use as observations these Hadcrot-3 observed monthly surface temperatures from 1970 to 1999. So we're just trying to predict monthly mean temperatures. This analysis of observations is on a 5 degree by 5 degree grid. And it's shown here that where you see the white cells, that's just where there wasn't enough data to actually make an estimate of what the monthly mean was. Where you see the color, there was an estimate. And the colors are actually showing the mean square distance from this sample mean. So in this case, all in the uppermost diagram, all these colors refer to, if I just take the sample mean of the CMIP3 ensembles, you can see I get these big red colors corresponding to numbers like 4. That's just showing that the sample mean of CMIP3 forecasts for these monthly average temperatures they're a long way away from the monthly mean averages of the OBS. Whereas if we do our technique, they get much closer to those. Now we're down in sort of the greens, their values like 3s and 4s. So, and we did this test with we train on all of the years except 1, and then we test on that year that wasn't used in the training data set. So there's an out of sample aspect to that test. And so this is another way of describing it. So these are the results of, so for the test, you can choose to take out different years and let those different years be the test year. So you train on every year except 1, and then you test on this remaining year, and you get different mean square distances over the whole globe, depending which year you use, and then you can fit distributions to that. So this black line here, this is what you get if you do just the simple multi-model mean of the CMIP3 ensembles. And you can see here the mean square error is up around 1.9 or something, whereas if you do the method I just showed you, this ensemble dependence transformation, the errors are way down here, like 1.3. So you get this really big improvement in the distance from the observations. So accounting for the intermodal error correlations, which is basically what this technique does, gives greater improvement than basing weights solely on the error variance of each model. I didn't really talk about, there'd been other work done where they try and define these weights based on error variances of each particular model. And so our method considers the correlations of the errors of every model with every other model. You have to do that to find the minimum error variance estimate, by the way. And then another thing you could do, suppose you didn't have any models, all you had was the observations, then what you could do is just take the mean of all the observations except the year that you're testing on. And if you did that, this is the mean, this is the distribution of errors you'd get over all the tests you performed. And you can see that the mean value of that has a bigger error than what we got from the models. So there's some benefit from using the models. It's also, there's a very big range of error variances there. So there's also this rank frequency histogram test. The idea here is, like, if we had an ensemble of replicate Earths, let's say we're forecasting temperature in Melbourne, there'll always be a ranking from small temperature to a high temperature. You know, one of the members will forecast a cold temperature and one will forecast a high temperature, and it'll be going, you know, from low value to a high value. And then there'll be reality. Reality will come in somewhere. And what you want is the ensemble members to be indistinguishable from the truth, statistically. If that was the case, that would mean, you know, if I do 100 forecasts, then, and let's suppose I've got 10 ensemble members, then 10 out of those 100 times, on average, the truth would have the lowest rank. It'd be the coldest. But then there'd be another 10 times where the truth would be the second coldest. And there'd be another 10 times where the truth would be the third coldest. So basically, if you have an ensemble forecast and then you grab the obs and then pretend the obs are part of the ensemble forecast, but then pay attention to what rank the ob turned into. So was the rank the coldest forecast, in which case it'd get rank 1, or if it was the second coldest, it'd get rank 2, third coldest rank 3, etc. And so you just compute the frequency with of these ranks that the actual observation takes. And what you want is for that to be flat, because if that's flat, then you can say, I can compute probabilities from this ensemble forecast. When my ensemble forecast, say if I've got 100 members and 10 of them say that event A will happen, then I can say, well, there's a 10 out of 100 chance of that happening. I can believe the frequencies coming out of the ensemble are equal to the probability of that event happening. And so this actually worked out really well for this method. So we were getting reliable probabilities. That sort of just describes what I just said. And this is kind of a similar story. And so that was there. It wasn't really much of a forecast test. We were just using historical data. So it was just from, you know, 30 years preceding 2000. But now we're going to do something a little bit more challenging. Of course, we don't know what the climate's going to be like in 2100. We don't know what the concentration pathway will be. We don't know any of this. So how can we test its ability to give a reliable forecast in, say, the year 2100? This is what we're going to do. We're going to take an ensemble of some number K of the CMIP 5 climate forecast initialized in the late 1800s and subject to prescribed future greenhouse gas forcing scenarios. And then what we'll do is just take one of those members, kind of remove it from the ensemble, and replace the real 20th century observations by pseudo observations from one of the models. Does that make sense? So instead of using the real observations, we're going to take the values from one of the models and pretend they are observations. Yeah? And we're going to use those pseudo observations from that model to derive this ensemble dependence transformation weights. Does that make sense? So the beauty of this approach is we know what that model looks like in 2100. Yeah? Nick, you're frowning. You have a question? No?
Working it out. I think I'm there.
Yeah? Does that make sense? So it's just like, right. Yeah. Yeah, it's just the idea of, so, you know, you make observations out of one of the these forecast trajectories, and then we can take the observations from the last 30 years of the 21st century, train these weights, and then apply that to all the other ensemble members, and then see if that weighted ensemble can predict that model that was left out of the ensemble at the end of the 21st century. Okay, so, and then we can do that for every single model in the CMIP5 group, yeah? So we can have, if we've got 100 ensemble members, we can have 100 independent tests. For each, there are these different concentration pathways that, depending, that the IPCC put together, and different centers contributed different numbers of members to each of those concentrations. So we had to each of those concentration pathways. And so we had different ensemble members for each of those, but we could always apply the technique. And if we did that, so that we call these model as truth experiments, because we're pretending just one of the models is a truth and it's not in our ensemble. And so if we look at this root mean squared distance from the verifying observations for the 21st century, then we're seeing a range of improvements. We get a distribution because we can use different models as the truth, but on average it's about 30%. So we train on the 20th century and test throughout the 21st century. Histograms show improvement in the ensemble mean, root mean square distance over using all possible models on truth. In all 301 trials, this ensemble dependence transformation mean had smaller RMSD than the CMIP bias corrected mean. On an average, that root mean square difference was 32% smaller. So each one of these is a different concentration pathway with a different set of models in it, but so it helped a lot. The other thing we want to check is how well are we predicting the standard deviation in the 21st century. And this is showing, because we have this model, we can estimate what the standard deviation of the CPDF associated with the model is. And so this shows how much better we do by doing this transformation. And on average, it's really big. There's this one outlier where we actually did worse, but it turns out, what was the deal with this model? This model was actually had terrible performance compared with the actual observations that of the 20th century. So I don't know, that it didn't work for all of them, but it certainly worked for most of them. So for the majority of cases, this ensemble dependence transformation predicted the future climate probability distribution standard deviation better than the bias corrected CMIP ensemble, and the mean improvement was about 50%. I guess the other thing I'd want to say about this was using the observations makes it consistent with what's been happening now. And you can always ask the question of like, well, things will be so different 75 years from now. The observational record we have now mightn't be relevant. You can put that on it. But suppose you want to do a decadal forecast. Now we're only talking 10 years ahead. So it's like, and what else do we have to go on apart from, the observations we have now? So I don't know, I think it's a fair thing to do. This is just showing, so in the gray, these are different representation concentration pathways. So in this one, the greenhouse gas, so this is the temperature on the y-axis, and this is time on the x-axis. And you can see for different representative concentration pathways, there's different amounts of warming. And what we're comparing here is the raw spread you get from the CMIP ensemble, bias corrected. And you can see in this example, it's the gray line. It's not showing up terribly well in the figure, but the gray line, you can see its variance is much bigger. And the red gives what you get after you've done the ensemble dependence transformation. You can see it gives a smaller variance. And that's kind of true for all these different pathways. We get a somewhat smaller variance, but There's not a huge difference in where the mean's going. I mean, it's a little bit colder there, but the main impact actually is more on the variance, and the CMIP5 ensembles are more spread out.
Right, sorry.
Yeah.
How do they do the bias correction? And does that add to the variance?
No, they just do the bias correction so that it sort of matches up with on average, it's consistent with the observational record. It's just one number. So no. Yeah, it could do that, but it doesn't. Yeah, what do I want to say? So this is kind of, when you take these CMIP ensembles, their spread, it doesn't necessarily represent a likely variance of our planet. When I saw this diagram, we haven't done this yet, but it made me think about the idea of like, maybe we should be thinking about, instead of just like this one CPDF, we should be thinking about ways of generating ensembles of CPDFs. So like at the moment, we just sort of have this individual model and that's what we focus on. But maybe we should think about it a little bit differently, that there be kind of an ensemble of these CPDF. I mean, in this case, the CPDF is really just sort of this mean and this outer spread. That's what we're describing it with. But you could imagine ensembles of that. But anyway, the main takeaway is you get slight differences in the final mean, and definitely the variance is smaller. So an ideal ensemble would sample the climatic probability distribution. The instantaneous climate probability distribution and its variance are formally unobservable, but can be plausibly estimated and predicted by applying the EDT to ensembles of models of the quality found in the CMIP5 ensemble. The Earth replicate ensemble defines the climate probability distribution, but in a sense is imaginary. Nevertheless, it provides a framework for understanding the role of chaos in climate prediction, provides properties that ensemble post-processing schemes should aim to emulate. The application of the ensemble dependence transformation to the CMIP5 ensemble led to forecast ensemble means with marked reductions, 30% on average, in the root mean square error. It also greatly improved, 50% on average, the prediction of the variance of future climate probability distributions. Thank you.
Thank you, Craig. And we have time for some questions. So, oh, Malta, I saw you first, sorry.
Yeah.
Craig, thank you. Fascinating. Not that I understood everything, but on the last slide that you had there, why would you expect, like, for a lower scenario RCP 2.6 being a downward adjustment, and then for the next higher, the RCP 4 or 5, an upward adjustment? Is that due to the fact that the ensemble of CMIP5 models producing these ranges is different?
Yes, exactly. So Gab actually looked at that in some detail, and he thought that was exactly why.
Okay.
Right.
And the other question was, if you take your perfect model worlds as an approximation for how well the technique is doing, and then say, okay, we can produce a CMIP5 or CMIP6 ensemble for these scenarios and get a better projection. Sometimes more, and we do this by using observations. Sometimes the models differ from observations for explainable reasons. For example, they have a different aerosol, and they have a much too strong aerosol. So there's a downward bias from the model from actual observations. But you know the reason, and if you now would shift the model upwards, then it might better match with historical observations, but it would possibly do worse in the future because A, aerosols go away, and B, you would adjust it for a reason that you could much better adjust by going through the process. So sometimes you might then adjust models for something that you can explain otherwise, and so models might be wrong for the right reasons?
So all of these models, before we put them into this technique, were bias corrected. So, you know, if you had some model that was way too cold because it had way too much aerosol in it or something, then that would be bias corrected, which would probably mean that it would end up way too warm later. So we kind of did that. But yeah, no, you could get, I think you're right, you could get more fancy with how you might adjust for knowledge about what's specifically wrong. But then you're making assumptions that you really understand exactly how it will behave, you know, if you took that part out of it. Yeah. I think your question raises the issue of, so one thing we're really interested in is climate sensitivity. Yeah, so how much will it warm? And so here we're using very simple metrics, so just the temperature. But you could think if what you care about is climate sensitivity, you could try and use metrics where you think there's more likely to be climate sensitivity. So one would be ice extent. So typically, you know, in springtime, that's the maximum of ice extent, and in the autumn, that's the minimum. And so that's sort of telling you something about how well does the model do in sort of changing this ice extent, which we expect that to have a lot to do with climate change. Another one would be these cloud banks, these low-level clouds. How good a job does it do with things like that? You could choose other metrics, and then, you know, we've bias corrected it. The thing about just having the aerosols all off, that's so difficult, isn't it? If they've got some completely bogus aerosols and then you have all the aerosols go away, then yeah, that'll give you a big warming. Just like,
okay.
Yeah.
I think we'll go to Ewan and then Penny after that. Is that okay?
Yeah.
Okay, thanks, Craig. So the CMIP models aren't behaving, or the CMIP model ensemble isn't behaving like this sort of idealized replicate Earth ensemble.
Yeah.
Do you guys have any reason or understanding as to why that is? Is it because they're all sharing the same assumptions, or they're not resolving, you know, all the physical processes that, say, a real replicate Earth ensemble would resolve?
Yeah, I think you've kind of given the answer. Yeah, so we all read the same literature. Yeah, so we're making, there's a lot of similar assumptions when we do physical parameterizations. That could be a reason you get these blocks of correlation between the models. I mean, there's sort of a combination, because on one level we're seeing too much correlation, but we also see too little correlation as well. So there's a bit of both, whether it might be that imagination is actually giving us more diversity than reality would. But I mean, other common things are where none of us are resolving the subgrid scales. Yeah, so there's some effect that subgrid scales have that we're all missing in probably a very similar way. I mean, we try and compensate for that for parameterization schemes, but there may be common bits there to it as well. Yeah, it's basically, you know, because they're all imperfect, and I think we can all think of many reasons why they're imperfect. Yeah.
You know, thanks, Craig. That was really interesting, and I think I understood it, having played around with some things like this in the past. A bit related to the previous question, I can imagine you could you break up your CMIP ensemble into sort of separate classes in some sensible way? Maybe it's on the parameterization schemes they use. If you could have, say, two families of models, or the high resolution versus the low resolution ones. Could you do all of this exercise on some sort of partition? And that might teach you perhaps a little bit more about where these differences are coming from, and if they're mainly associated with particular types of models. Alternatively, have you done it for CMIP 3 versus CMIP 5? That would be interesting, is to see whether you get the same results there. And what do you see going on with regional changes? And even moving to something like precipitation. Sorry, there's a lot there.
No, So I sort of mentioned that at the end. I like the idea of breaking the ensemble into subclasses. I kind of feel like the real uncertainty we should be thinking about is the uncertainty in the climate probability distribution. So at least the mean and a variance, and those two things should go together. So, you know, we have this thing where we do individual models and but that's not what we want. We want an ensemble. I think for this problem, we want an ensemble of climate probability distribution. So instead of, you know, I just gave you one. I gave you this red line, the bright low red line, and I gave you that sort of rose width there. That's all I gave you. I mean, in a way, I think it would be better to say something like, here's a distribution of possible CPDs. And as you were saying, you know, if you all took a certain parameterization scheme, it might be one class of parameterization schemes actually gives you a lot more variance, yeah, in the CPD. And that would be really important. I think it's more difficult to manage a world where there's a lot of variance than there is to manage a world where there's less variance, yeah? So it's kind of, that's important to know. So I'd love to apply this technique to in a similar way to what I think there'd be interesting things to learn from that. What pulls me away from that a little bit is one of the reasons we were able to get those massive reductions, I don't know, in a weather forecasting sense, they were really big reductions in the root mean square distance from observations, is from this thing of independence. So there's just this very simple thought experiment. Yeah, if you've got some normal distribution, yeah, and suppose you're trying, and truth is just a random draw from that distribution. You just pull a random number from a normal distribution, you call that the truth. And then your forecast is going to be a random draw from just the same distribution. In that case, that variance goes from, if you just take the two by themselves, you've got that error variance is twice the variance of the distribution. And if you take two, then you halve that. Another way of describing it is, sorry, like if each model was the truth plus a random error, then, and each model was equally skillful, then each time the actual variance of the mean there would be 1 on n times the error variance of the individual model. So there's these little calculations you can do that having independence really helps. And the problem is if you choose all the same parameterization scheme, that you don't have the independence anymore. So I'm a bit struggling with that thing of like wanting to see like different CPDs, but still having the independence. And I haven't quite got to a point where I feel comfortable how to approach that. Yeah, Kim. Sorry.
Have you tried your method on non-parametric and non-Gaussian distributions like rainfall?
No. But the basic principles still apply. So what I said about the mean and variance, that's absolutely fine for a gamma PDF or a log normal. That idea is the same. If you have really big skewnesses in the distribution, there can really be a problem with the sample size because you won't sample the tail. You just get unlucky. But principle shouldn't be too bad. Yeah.
We probably have time for one more. Andrew, up the back.
Thanks. There's lots of really interesting implications, I think, from what you've showed, Craig. But I'm just wondering what exactly you would advocate for in terms of climate projections work based on these results. So what I would interpret your conclusions as meaning is that, you know, for making some simple climate projections, maybe we should be using this kind of method, but for trying to understand the processes, and this is kind of going towards what Malta was saying, if we're trying to understand the processes behind differences in climate projections, we probably wouldn't use this kind of method because we don't want to remove or account for some of those differences. But what would you say?
I don't think it's a either or situation. I think, you know, by separating the forecast into different classes, this might actually help you identify, you know, where the differences are coming from. I think in terms of trying to say something about what the temperatures will be, this is, you know, what people have to build for. This seems much more, it would be quite useful. I guess the other thing in terms of a community, just sort of some of the tests we had there is like, you know, particularly when it comes to ensemble post-processing or interpreting this big ensemble, how you try and say that of what climatic conditions will be like at the end of the next century. I'd love to see there be more agreement amongst the community about what sort of tests to do. So this, you know, using a model as truth, like for example, in weather forecasting, everyone looks at 500 hectopascal anomalies. You know, there's a few measures that everybody looks at. It'd be nice to have some of those for climate. And so that, you know, somebody comes up with some new method or whatever, and you can see, well, how well does it do on that measure? And we could actually compare with each other, because there's actually a growing body of literature in this whole thing of climate ensemble post-processing. And at the moment, you know, you read through the literature, well, they're kind of looking at something a bit different to what I did. And, you know, it's just really hard to compare. So that, yeah.
Okay, I did say that was the last question, but we have one online from Neil, and then this will be the last one, I promise. Neil?
Thanks. Thanks for the presentation.
Can you hear us, Neil?
Hello?
Maybe not.
Hello?
Neil, it's your turn.
No.
Hello?
Okay. Well, then I didn't lie, and that was our last question. So join me in thanking Craig again. And then there is a slide of our upcoming seminars. I don't know how to find it. We have 2 seminars next Monday, one at 2:30 and one at 6:30. We have Neil Craig at 1:30, and I can't quite remember the title, and Eliza DeWitt at 6:30. And then another one on Wednesday. So if you'd like the information about those, please go to our website, which I think Malta is bringing up right now. No. Okay, just check our website. But on Monday, we have 2 very interesting seminars coming up, so please come back. Thank you.